Ever wondered how airplanes defy gravity and soar in the sky, or how ships, heavier than the water they displace, don't sink? Welcome to the fascinating world of fluid mechanics. Now you might be wondering, what exactly is fluid mechanics? Well, in a nutshell, it's the science that studies the behavior of fluids, both at rest and in motion. And when we talk about fluids, we're including not just liquids like water, but also gases like air. So, whether it's a stream flowing down a mountain or the wind blowing through your hair, that's fluid mechanics at work. But fluid mechanics isn't just about observing and understanding nature. It's a fundamental part of our daily lives and technology. It's in the way our cars move, the way our buildings are designed, even the way our blood flows through our bodies. Yes, you heard that right. Your heart is essentially a pump, and your veins and arteries are a complex network of pipes. So, in a sense, we're all living, breathing examples of fluid mechanics. Now let's take a moment to appreciate the sheer scale of fluid mechanics. From the tiniest droplets to the vast oceans, from the slowest creeping lava to the fastest jets, fluid mechanics is everywhere. It's in the way the Earth's atmosphere circulates, creating our weather. It's in the way the planets and stars move in the cosmos. It's the key to understanding and harnessing the power of nature. And let's not forget about its role in technology. From designing efficient cars and planes, to harnessing the power of wind and water for renewable energy, to creating life-saving medical devices, fluid mechanics is at the heart of innovation and progress. So whether you're a student looking to dive into this fascinating subject, an engineer seeking to hone your skills, or just a curious mind eager to understand the world better, you're in for a treat. Now that we've piqued your curiosity about fluid mechanics, let's delve deeper into the subject. So, what exactly is fluid mechanics, you may ask? Well, let's dive right in. Fluid mechanics is the branch of physics that studies the behavior of fluids, both at rest and in motion. It's all about understanding how fluids, which can be liquids or gases, behave under different conditions and forces. Now, fluid mechanics is divided into two main branches. First, we have fluid statics, which deals with fluids at rest. Think of a glass of water sitting on your table, or the air in a room. The second branch is fluid dynamics, which is concerned with fluids in motion. Imagine a river flowing or wind blowing through the trees. So, in essence, fluid mechanics is a fascinating field that helps us understand and predict the behavior of all fluids around us, whether they're moving or still. Understanding fluid mechanics is like having a secret key to unlock the mysteries of nature and technology. Now let's uncover the three fundamental principles of fluid mechanics. Imagine you're a detective, and the crime scene is a fast-flowing river, or a steam-powered machine. The clues you need to solve the mystery lie in the principles of fluid mechanics. There are three key principles to consider: conservation of mass, conservation of energy, and conservation of momentum. First, let's talk about the conservation of mass. Often referred to as the continuity equation, this principle suggests that mass cannot be created nor destroyed. It's like a detective knowing that nothing can magically appear or disappear from the crime scene. In the context of fluid mechanics, it means that the mass flowing into a system must equal the mass flowing out, regardless of the system's complexity. Next, we have the conservation of energy, or the energy equation. This principle states that energy cannot be created or destroyed, only transferred or changed from one form to another. It's like saying, if our detective finds a burnt matchstick at the crime scene, energy in the form of heat was released by burning the match, but the total energy before and after the match was lit remains the same. So, in fluid mechanics, the energy of a fluid particle remains constant unless energy is added or removed, like through work or heat. Lastly, we come to the principle of conservation of momentum, also known as the momentum equation. This principle is about the balance of forces in a fluid, stating that the rate of change of momentum in a system is equal to the sum of external forces acting on it. Picture our detective watching a ricocheting bullet. It changes direction due to the forces acting upon it. Similarly, the behavior of fluid flow can be predicted by understanding how forces affect the fluid's momentum. So there you have it, the three fundamental principles of fluid mechanics. They are like the detective's toolkit, giving us the means to understand and analyze the behavior of fluids in any situation. With these principles, you can begin to unravel the complex behaviors of fluids. Imagine a world at rest. Let's explore fluid statics. Fluid statics, or hydrostatics, is an intriguing aspect of fluid mechanics that delves into the behavior of fluids at rest. This branch of science focuses on the forces exerted by static fluids. It's a world where the fluid isn't flowing, but that doesn't mean it's devoid of activity. Now let's tackle the concept of pressure. Picture a diver deep underwater. The deeper they go, the greater the pressure exerted on them. This is because pressure is the result of the weight of the fluid above pushing down. It's just like the saying, it's not the fall that gets you, it's the sudden stop. In the world of fluid statics, it's not the water that gets you, it's the weight of it. Pressure is a force exerted by the substance per unit area on another substance. It's a scalar quantity, meaning it only has magnitude and no direction. In the realm of fluid statics, we often use the Pascal as the unit for pressure, named after the renowned French mathematician and physicist, Blaise Pascal. Next, let's dive into buoyancy. Ever wondered why some objects float while others sink? It's all thanks to the principle of buoyancy. This principle states that any body submerged in a fluid experiences an upward force equal to the weight of the fluid it displaces. So if you've ever been thankful for floating in the ocean rather than sinking to the bottom, you have buoyancy to thank for that. It's fascinating to realize that even when fluids are at rest, there's a lot going on beneath the surface. Understanding fluid statics is like learning a new language, the language of static fluids. It opens up a whole new way of seeing the world around us. From understanding why we feel pressure in a deep pool to why a ship floats on water. Fluid statics is a crucial building block for understanding how fluids behave when they're at rest. So let's continue our exploration of fluid mechanics, where the world of static fluids unravels more fascinating phenomena waiting to be discovered. Now let's set the world in motion. Welcome to fluid dynamics. Fluid dynamics is the branch of fluid mechanics that studies the behavior of fluids in motion. It's like the choreographer of a ballet, orchestrating the dance of fluids as they flow and interact with their surroundings. But instead of music and dancers, fluid dynamics uses principles of physics and mathematical equations. Let's start with a fundamental concept, flow rate. Imagine a river. The flow rate isn't just about how fast the water is moving, it's about how much water is passing through a given area in a certain amount of time. In technical terms, it's the volume of fluid that passes per unit of time. It's like the rhythm of our fluid ballet, dictating the pace at which the dance unfolds. Next, let's explore Bernoulli's equation. This principle is a statement of the conservation of energy principle for flowing fluids. It's named after Daniel Bernoulli, a Swiss mathematician who lived in the 18th century. Bernoulli's equation tells us that as the speed of a fluid increases, its pressure decreases. It's like the leaps and bounds in our ballet, where the dancers, or in our case the fluid particles, rise and fall, creating a mesmerizing spectacle of motion. But what about the resistance we feel when we move our hand through water or when we stir honey with a spoon? That's due to a property called viscosity. Viscosity is a measure of a fluid's resistance to shear or flow. The higher the viscosity, the thicker the fluid and the more energy it takes to move it. It's like the tension in our ballet, the push and pull that adds drama and complexity to the dance. Understanding fluid dynamics isn't just about knowing the steps of the dance. It's about understanding how and why the dance unfolds as it does. It's about predicting the movements, recognizing the patterns, and appreciating the intricate interplay of forces that shape the fluid world. But why is understanding fluid dynamics important? Well, it has countless applications in our daily life, from the blood flowing in our veins to the oil in our cars, the water in our pipes, and the air flowing over our airplane wings. By understanding fluid dynamics, we can design better medical devices, build more efficient engines, create more sustainable energy systems, and even predict and manage natural disasters like floods and hurricanes. Fluid dynamics is a fascinating field that combines physics, mathematics, and engineering to help us understand and harness the power of the fluid world. It's a dance of nature that's happening all around us, all the time, shaping our world in ways that are both subtle and profound. Fluid dynamics helps us understand how fluids move and interact with their surroundings. So the next time you see a river flow, a faucet drip, or a wind gust, remember you're witnessing a ballet of fluid dynamics in action. Let's bring fluid mechanics out of the classroom and into the real world. When you sip your morning coffee, fly in an airplane, or drive over a bridge, you're experiencing the magic of fluid mechanics. This field of study is not just confined to textbooks and lecture halls. It's all around us, shaping and influencing our daily lives. Take a look at the aerospace industry, for instance. The principles of fluid mechanics are what keep airplanes aloft. When an airplane flies, the air flowing over and under the wings creates lift, enabling the plane to stay in the air. The design of the airplane, from the shape of the wings to the placement of the engines, is all influenced by fluid mechanics. Even the way pilots adjust their flight paths in response to changing wind speeds and directions has roots in this field. Moving on to civil engineering, fluid mechanics plays a crucial role in managing water supply and waste disposal. It helps engineers design efficient plumbing systems that deliver clean water to our homes and dispose of waste safely. Think about the last time you turned on a faucet or flushed a toilet. The water flowing out and the waste being carried away are all governed by the principles of fluid mechanics. But let's not forget the medical field. Here, fluid mechanics is instrumental in understanding how blood flows through our bodies. This knowledge is critical in designing medical devices like heart pumps and dialysis machines. It's also used in developing treatments for conditions like atherosclerosis, where the flow of blood is restricted by the buildup of plaque in the arteries. Even in the realm of sports, fluid mechanics is at play. It helps design more aerodynamic bicycles for cyclists, enables swimmers to understand how to move through water more efficiently, and even influences how golf balls are designed to fly farther and straighter. And these are just a few examples. From the oil and gas industry to environmental science, from fire safety to designing wind turbines, the applications of fluid mechanics are vast and varied. It's a cornerstone of modern life, silently shaping the world in ways we often take for granted. So the next time you're drinking a cup of coffee, remember that the flow of the liquid into your mouth, the steam rising from the cup, even the pressure that forces the water through the coffee grounds, they're all examples of fluid mechanics in action. It's not just a subject you study in a classroom, it's a fundamental part of the world around us. These examples underline the importance of fluid mechanics in shaping the world around us. We've just scratched the surface of the vast and exciting world of fluid mechanics. It's a universe of knowledge that's as deep and flowing as the subject matter itself. We've taken a journey from the basic understanding of what fluid mechanics is to the fundamental principles that govern this fascinating field of study. We've seen how the calm world of fluid statics can captivate us with the mysteries of liquids and gases at rest, how it's the bedrock of many engineering marvels we see around us. We've also dived headfirst into the thrilling realm of fluid dynamics, understanding how fluids in motion shape our world, from the natural phenomena to the man-made wonders. But remember, all this is just the tip of the iceberg. There's a whole ocean of knowledge waiting to be explored, each wave bringing with it new and exciting real-world applications. From designing efficient fuel systems to predicting weather patterns, fluid mechanics is a key player in shaping the future of engineering and technology. As we navigated through these complex waters, we hope that this video has ignited a spark, a desire to learn more, to delve deeper. This field of study is not just about equations and principles, it's about understanding the world around us, the invisible forces that are constantly at work. And with that, we come to the end of this exciting exploration. If you found this journey enlightening, if you've enjoyed this video about fluid mechanics, why not give this video a thumbs up? Your likes are the compass that guides us in creating content that you love. And if you're already a part of our VIP-loving community, thank you. You are the wind beneath our wings. If you're new here and you found value in this video, consider joining the family. Hit the subscribe button and the bell icon to ensure you never miss out on a new mechanical engineering core course video.